drive of some sort. So it's really, I don't necessarily believe that I see the distinction between those two. I mean, do you guys? I don't know why they distinguish it, because maybe it'll become apparent to me as I reread the section sometime, so. Okay, after this, let's see, what else do we have? We have a cylindrical joint. Well, a cylindrical lower pair. What's the motion going to look like in this case? If it's cylindrical, the workspace is going to look something like that, where we move up and down and then position the link around a revolute joint. So what are the characteristics of a cylindrical lower pair? It has both a prismatic component and a revolute component. So this actually has 2 degrees of freedom. We could model it as a prismatic and revolute compound joint. Otherwise, what you'd have to do is have 2 variables in your transformation controlling this. That makes sense. Okay, what other types do we have? Say again. Well, this is the basis for a scalar robot. In fact, a scalar robot provides a prismatic joint which has your Z and then a theta angle associated with it. And then you'll have a second segment that provides your 3rd degree of freedom. And then your end effector will have a 4th degree of freedom that is responsible for the orientation on the end effector. So you'll have 3 degrees of freedom providing position and 1 degree of freedom providing your orientation of the end effector. That makes sense? So yeah, this is at the heart of the SCARA robots. So. Okay, so the one other, or actually 2 other types. One of those 2 other types is a planar robot, or planar lower pair. This is distinguished from the planar robot that we're going to be modeling this next week. This likewise has 2 degrees of freedom. In fact, we could probably say that we have a spatial lower pair with 3 degrees of freedom. What would that be similar to? This would just be represented as a XY stage. In the case of a spatial lower pair, we'd have a XYZ carriage. So that'd be real similar to what you see on a CNC or a lathe of some sort, where you typically have 2, well, not the lathe, but the CNC mill or the CNC router that's in the workshop. So, okay, both of these are prismatics. And it's very, very unusual. In fact, I'm not sure I've ever encountered it to see these prismatic joints not be orthogonal to each other. That really wouldn't make a whole lot of sense, having a planar robot that does not have orthogonal axes associated with it. Okay, and then the final lower pair is our, let's see, prismatic. That's not right.
Spherical.
Spherical, yeah, sorry. And In this case, we have 3 degrees of freedom, and they're all revolute. So in this case, this would go right back to the XYZ fixed angle or the ZYX Euler angle representation that we just got done talking about. Again, more than likely, we would not model this as a single transformation, but as a series of compound transformations.
What kind of lower pair was that again?
Say again.
What kind of lower pair was that again?
That's a spherical. Yeah. Okay, so with that then, this is the basic, the types of lower pairs that we'll be interested in. And as I've said many times up until now, we're going to only really concern ourselves with revolute and prismatic, because all of these others can be expressed as compound operations of these 2 basic joints or basic lower pair configurations. So let's take a look at what these links and lower pairs will look like. All right, so I always have to practice drawing this every quarter. Okay, so this is a really poorly designed link attached to 2 joints on our robot. What are the different characteristics that you notice here? Well, from one joint, first off, where would the, how would the joints be oriented? How would we define the frame rotation of each of the joints? So this would be our, I'm sorry. This would be our positive X, this would be our positive Y, following the right-hand rule, and our positive Z goes through the center rotation on that joint. We can do that for each of our joints on our robot. If it is a revolute joint, we know that each and every time we're going to pass Z immediately through that joint. We're going to assign X pointing in the direction of the subsequent link, and then Y will just complete the frame. What do you notice now that we've kind of defined the Z-axis in relation to each of those joints? I don't think that ever has helped. And obviously this one helped me either. Oh, there I go again. Oh well, that's it. So what are the descriptions of this frame? I'm sorry, of this lower pair. Well, which of these joints is this link associated with? Assuming that our end effector is over there somewhere.
The first one.
The first one. So we could assign this as the K link the kth joint and its corresponding kth link. Okay, that would then make this our kth plus 1 joint. Okay, so everything that we're going to do is going to be in regard to describing this kth link. Okay, this could be the first, second, or third. What do we probably need to know?
Where the origin is?
Okay, well, the origin we can place somewhere along the z-axis. Okay.
Well, I thought you meant like the relation to the origin, like the base.
Yeah, absolutely. What we're probably going to do is define the origin conveniently, say, at the center mass on that joint. I mean, that's just kind of arbitrary, but that would make sense, right? What do we need to know in describing this lower pair? There are 4 things that we can identify here. So, tell me something that you can identify from this.
Transformation of our, what is it? Our grid from joint to joint, or like X, Y, and Z. the
Okay.
change of it.
So we can definitely determine the length of the joint. And that's definitely something that we need to know. We need to know how far it is from this joint to this joint, so we need to know the length of the link. How are we going to go through and measure that distance? That distance is referred to as, well, they call it alpha, or A, but in our case, we'll call it R, just to make sure that we distinguish it. So this will be our radius of travel, and it is the distance or length of the joint along the x-axis. Okay, so that's just telling us the length of the segment. That makes sense? What else can we go through and determine? And by the way, which, well, I kind of represented there. Oh, I even said it there. So this radius is always measured along the x-axis. We always point this x-axis in the direction of the subsequent link. It's pointing right down the arc. That provides a single element that we can perform a transformation around. So it's a single characteristic. Okay, what else can we determine?
The angle that the two z-axes are displaced by.
So we can go through and figure out what angle of rotation this first joint went through in order to get to our second joint. Okay, so we can look at the angle from our kth joint to our kth plus 1 joint. Okay, so our alpha is the angle from kth to kth plus 1 joint. What else then? And we're almost out of time. We're going to be spending plenty of time on this. Next thing we can go through and look at is well, what we need to do is figure out if there's any z offset between this joint and this joint. So what we do is we go through and draw a normal from our kth+1 joint back to our kth joint and use that normal to determine if there's any displacement on the z-axis. Now with that, we can see that only the x distance on our kth joint and then this new z parameter on that kth joint are of interest to us. So this z displacement provides our two linear displacements from our kth to our kth+1 joint. Okay, and finally, what we need to do is define a second angle, and the second angle I didn't bother to write here. The second angle is the angle, I need to go through, I can't read the drawing there, but the second angle is the angle that separates the normal from the kth+1 x-axis. So tomorrow when I draw this up there, I'll draw in each of these parameters a little more appropriately so that we can go through and take a look at it. These four parameters are what are known as the DH parameters, the Vannevar Hardenberg parameters. These were actually developed in the 60s by two PhD candidates at Stanford University down in California. And they've since become like the way of parameterizing these lower pair descriptions. So with that, then what we'll do is we'll come back in tomorrow, develop this idea of how we can go through and describe these lower pair joint link combinations. With that, then we'll be able to come up with the transformation used universally for both planar and spatial robots. And from there, then we'll be able to go through and write the function for that transformation, and we'll have the heart of our programs for the rest of the quarter. So, questions? I honestly didn't think we'd get this far this lesson, so that's kind of why I was a little bit shaky on this stuff. So, anyhow, I will see you guys tomorrow. So.